Hey, just a quick video about forces moving on forces on a charge moving through a magnetic field. It's quite similar to the previous one on forces on a current moving through a magnetic field because it's basically the same idea. We just kind of apply it a little bit differently. So it is basically a current just without a wire. A moving charge, like if we have a magnetic field and a current moving through it, okay, we can use the right-hand rule where the fingers are the magnetic field and the thumb is the direction of the current, and palm is the direction of the force. Palm in this case would be facing upwards, so there is a force upwards. Okay, so that's just the normal right-hand rule. But if we think about some definitions, a current is a flow of charge. And when we talk about, in this situation, we talk about conventional current. Conventional current is the direction of flow of positive charge. So there's no rule that says a current has to be in a wire. So if we, instead of having like a current flowing through a wire, if we just had a positive charge moving, okay, that is conventional current. Okay, a positive charge moving is a conventional current. So that will experience a force in the same way. Okay. Now, a positive charge moving to the right like that is the same thing as a current moving to the right. So you can use the same right-hand rule. Okay. So your fingers pointing into the screen, thumb pointing to the right, your palms facing up, so you get a force on that charge upwards. Okay. But it doesn't have to be a positive charge. What if it was a negative charge? Okay. So remember, a moving negative charge, like electrons flowing through a circuit, is actually the same as a conventional current in the opposite direction. It will experience a magnetic force as a current, but the current is in the opposite direction when we're talking about conventional current. So that means because the current's in the opposite direction, the force will be in the opposite direction. Okay, and also in this, I'm sort of using that usual assumption that the magnetic field strength, the velocity, and the force are all perpendicular. So we're going to do the usual thing where we've got two things we need to sort out in this. What's the direction of the force and what's the magnitude of the force? So we'll sort out the direction first. So we use the right-hand slap rule, or at least a slightly modified version of it, at least the version that I use, okay? So the version I have, you've got your right hand is in the picture there. Okay? The fingers are the magnetic field, same as before. Lots of fingers, lots of magnetic field lines. The thumb, instead of being current this time, I use the thumb as the direction of the velocity, okay? The direction that the particle is moving. The palm is the direction of the force, okay? Now that's the direction of the force on a positive charge. The way I think about positive, if you do something positive, you get a pat on the back. If you're giving someone a pat on the back, you use the palm of your hand, okay? So pat on the back, positive, palm of your hand. And also positive and palm both start with P, okay? If it's negative though, it's the other way. So if you've done something negative, you get the back of the hand, okay? So a positive particle will experience a force in the direction of the palm, and a negative particle will experience a force in the direction of the back of the hand, okay? So let's actually see what that looks like. We've got a magnetic field, and we've got a particle of some sort that's moving into a magnetic field, okay? Now, if that particle was positive, okay, if we use that right-hand rule, fingers pointing into the screen, because that's the direction the magnetic field's going, the velocity is to the right at this point, and that leaves now it's a positive particle, so what direction is my palm facing? My palm is facing upwards, so that means there will be an upward force on the particle. So as the particle moves, an interesting thing happens. It'll move and it'll get deflected upwards, but as it moves, the direction of the force also changes. The force is always perpendicular to that magnetic field, okay? So we've got a force there that's changing direction and is always perpendicular to the velocity. That means that it shouldn't speed it up or slow it down, but also it acts as a centripetal force. So you get a circular path, okay? Because it's always perpendicular to the velocity. Now, if that was instead a negative charge, okay, we do the right-hand rule, we've got the same orientation, fingers into the screen. It's moving to the left, to the right initially. The back of the hand, because it's negative, the back of the hand is facing downwards. So there's a downward force on a negative charge, which means that it will be deflected in the downward direction. And the same thing happens because that force continually changes direction with it. You get a centripetal force, so it's a circular path. There's another case that we should consider, and that's what happens if it's neutral. What happens if there is no charge? Okay. Well, if there's no charge, there's no force. Okay. So a neutral particle will just travel through a magnetic field undeflected. Okay. And my usual reminder that remember that this is a right-hand rule. Don't use your left hand because you'll get things back to front if you do that. Okay. So here's some ones to try. If you want to have a go at these, I suggest pause the video, see if you can figure out what's missing. Remember, there are 4 things in these things now because there's a magnetic field, a direction of motion, of velocity, there's a force, and there's also whether it's positive or negative, because that affects what direction things are going to go. So pause it now, have a go at it, and then I'll go through the answers. All right, assuming you've had a go at that. So the first one, I'll just talk through these. The first one, magnetic field is to the left, so my finger's pointing to the left, and the circle with a dot indicates that that's the particle coming towards me out of the screen. So my thumb's pointing towards me, and my palm, now the force is downwards now, so which side of my hand is facing downwards? It's the palm that's facing downwards. Remember, the palm is the direction of the force on a positive charge. So that means number 1 there is a diagram for a positive charge. Okay. Number 2, now we don't know the magnetic field in this one, but we know we've got a charge moving downwards, so my thumb has to point downwards, and the force is to the right now, and it's a negative charge. So the back of my hand, the force is the back of the hand for a negative charge. So the force, my back of my hand has to face to the right, while my thumb faces downwards. That leaves my fingers pointing towards me, out of the screen. That means the magnetic field must be pointing out of the screen. Number 3, okay, magnetic field's upwards, and I've got a positive charge. Okay. So a positive charge means I'm interested in the palm of my hand, what that does, and the force is to the right, so the palm of my hand has to face to the right. That leaves my thumb pointing into the screen, away from me. So that means that that particle, that positive particle, is moving away from me. Number 4, we've got a positive particle moving to the right, so thumb has to point to the right, and it's a positive particle, so I want to know what the palm is doing. Okay, and palm needs to face down because that's the direction of the force, and when I do that, my fingers are pointing towards me, so the magnetic field is coming out of the screen. Number 5, a diagonal. The diagonal doesn't really matter, remember, because that's still perpendicular to the magnetic field. So we've got a magnetic field into the screen. My thumb's pointing up towards the top right-hand corner, because that's the direction the particle's moving. And it's a negative particle, so what direction is this back of my hand facing? The back of my hand is facing down towards the bottom right. So that's the direction the force will be in that case. And number 6, magnetic field to the right, velocity to the left. Please don't dislocate your thumb. There's no point because there is no force. Okay. If the magnetic field and the velocity are parallel, there is no force. Okay. All right, so that's all about the direction and how to find that using the right-hand rule. We also need to find the size of the force. Now, from last time, we're talking about magnetic fields on acting on wires. We have this formula, F equals Bill, where the force in newtons is given by the magnetic field strength in Tesla multiplied by the current multiplied by the length of the wire inside the field in meters. Now, I can actually replace in this. I'm just going to use this and substitute it, basically, rearrange it slightly to make a version of this that works for charges. We can replace current with charge over time. That's the definition of current, how much charge flows past in a certain period of time. So I can replace the I in that formula with Q over T. So I've got B times Q over T times L. Now, I can rearrange that slightly. I've just moved where I've divided by T, basically. I've just, instead of dividing Q by T, I've divided L by T, the length. So now I'm dividing a length, how far it travels, divided by time. That's a distance divided by time. Distance divided by time is a speed, okay? So this gives us a formula for the magnetic force on a moving charge in a magnetic field, okay? We take the magnetic field strength in Tesla, the charge in coulombs, and the particle speed in meters per second, multiply them together, and we get the magnetic force in newtons. Also note that formula only applies when B, V, and F are perpendicular. If B and V are parallel, the force is 0. Okay? So that's how we calculate the size of a magnetic force. And just a reminder, we use that sort of like slightly modified right-hand rule for finding the force. Okay, for the fingers of the magnetic field, the thumb is the velocity, the palm is the force on the positive, and the back of the hand is the force on the negative. There are other rules, by the way, for finding magnetic field forces, directions. There's lots of different versions of them, but this is just the one that I like to use. Cool. So that's me. Hope that helped.